we present unsupervised 3D shape completion through GAN inversion. 3D shape completion estimates the complete geometry from a partial shape, typically in the form of a partial point cloud. Most of the existing works are trained in a fully supervised manner with paired partial complete data. However, partial forms usually comes with different domains. While these methods achieve promising results for in-domain data, it's challenging for them to generalize to out-of-domain partial forms. In this work, we propose shape inversion, which applies GAN inversion to 3D shape completion for the first time. Specifically, we exploit the driver in a pre-trained GAN where no assumption on the partial forms are made. As the diagram shows, a latent vector Z is used by the pre-trained generator to reconstruct a complete shape XZ. The degradation function M then transforms XZ into a partial shape SP. The supervision signal includes both transfer distance and feature distance between XP and Xin, where the feature distance is computed using the pre-trained discriminator. Shape inversion looks for a latent vector and fine-tunes the generator that best reconstructs the complete output corresponding to the partial input via gradient descent. The key insight is that we address intrinsic challenges due to the nature of 3D data. Unlike 2D images that follows a grid-like structure, the unstructured nature of point clouds often leads to non-uniformity, which undermines the fidelity of our prediction. We thus propose a uniform loss called patch variance to regularize the density variance among randomly sampled local patches all over the object surface during pre-training. Taking tree-GAN as case study, which generates point clouds with tree-structured network, we group these generated points into branches by their parent nodes and colorize them for better visualization. For the tree-GAN baseline, nearly half of the points and 20 branches cluster in a single region. In contrast, uniformity is significantly enhanced with the use of patch variance. During the inversion stage, a good degradation mask is based on accurate and robust point correspondences between the partial input and the complete output. However, in view of the unordered nature of point clouds, such point correspondence is ambiguous, far less straightforward, and variant to different complete shapes. To this end, we propose K-mask to dynamically obtain the correspondences between the partial input and a specific output based on the Euclidean distance. Specifically, for each point Pi in the partial input, we look for its k-nearest neighbors from the complete output, denoted as the n function here. Consequently, xp can be constructed by the union of these k-nearest neighbors. As can be illustrated, K-mask achieves more accurate degradation compared to other intuitive designs that are based on predefined threshold. Our ablation study shows the effectiveness of patch variance during pre-training and the necessity of K-mask as well as the feature distance in the inversion stage. Shape inversion demonstrates compelling performance for shape completion in different scenarios. First, on the common benchmark derived from ShapeNet, it outperforms the state-of-the-art unsupervised method by a large margin, and being comparable to various supervised methods. Second, our method shows remarkable generalization ability and robustness when it comes to real-world scans or variation in partial forms, while existing methods show significant performance drop due to domain mismatch. Third, given more extreme incompleteness that causes ambiguity, our method is able to provide multiple reasonable complete shapes, all of which remain faithful to the visible parts presented in the partial input. Last but not least, we qualitatively show that our method achieves novel shape manipulation with plausible results for shape jittering and morphing. Thank you for your time.